What is time travel? Time travel has captured human imagination for centuries, appearing in countless books, movies, and TV shows. But what exactly is time travel? And is it really possible? At its core, time travel involves moving between different points in time, much like we move through space. But this isn't as simple as hopping into a time machine and arriving at a different year. The science of time travel is rooted in the theories of relativity proposed by Albert Einstein over a century ago. Einstein's theory of special relativity introduced the idea that time and space are intertwined into a single continuum known as spacetime. According to this theory, time is not absolute but relative, meaning it can vary depending on the speed at which an object is moving. This leads to the phenomenon known as time dilation. An object moving at a significant fraction of the speed of light experiences time more slowly compared to an object at rest. This has been experimentally verified through observations of particles traveling at high speeds and even with astronauts in space. For example, astronaut Scott Kelly spent a year aboard the International Space Station, orbiting Earth at about 17,500 miles per hour. Upon returning, he was slightly younger than his twin brother, Mark Kelly, who remained on Earth. This tiny difference in aging is a real-world demonstration of time dilation. The twin paradox is a thought experiment that illustrates time dilation. Imagine one twin travels into space at nearly the speed of light, while the other stays on Earth. Upon the traveling twins' return, they would be significantly younger than their sibling, despite having aged normally during the journey. This scenario highlights how traveling at high speeds affects the passage of time. Einstein's general theory of relativity further expands on the concept by explaining how gravity influences time. The stronger the gravitational field, the slower time passes. This effect, known as gravitational time dilation, means that time runs slower near massive objects like stars or black holes. For instance, if you were to spend time near the surface of a neutron star, time would pass more slowly for you compared to someone far away from such a massive gravitational source. While these effects are generally minuscule in everyday life, they have practical applications. GPS satellites orbiting Earth experience both special and general relativistic effects. They travel fast enough and are far enough from Earth's gravitational pull that their onboard clocks tick slightly differently than those on the ground. Engineers must account for these time differences to maintain the system's accuracy, ensuring that your GPS device can pinpoint your location precisely. Despite the fascinating possibilities, traveling back and forth in time as depicted in science fiction remains beyond our current technological capabilities. The primary challenge lies in the immense energy and exotic matter required to create and stabilize the conditions necessary for such travel. Time travel theory number 1. Time travel, a concept long explored in science fiction, has also been the subject of serious scientific inquiry. Several theories have been proposed to explain how time travel might be possible, based on our current understanding of physics. Here are some of the most prominent theories related to time travel. Time travel theory number 2. Special relativity. Special relativity is one of Albert Einstein's landmark theories, published in 1905. It introduced the idea that time and space are interconnected, and that time is relative depending on the observer's velocity. According to this theory, when an object approaches the speed of light, time slows down for that object relative to an observer at rest. This effect has been confirmed through experiments with particles moving at high speeds and with precise clocks on fast-moving aircraft and satellites. Time travel theory number 3. Closed timelike curves. CTCs. Closed timelike curves. CTCs are paths in spacetime that loop back on themselves, theoretically allowing an object to return to its starting point in time. These curves are solutions to the equations of general relativity in certain conditions, such as rotating cylinders, proposed by physicist Frank Tipler. A massive, infinitely long, rotating cylinder could create CTCs, allowing for time travel. Cosmic strings, hypothetical one-dimensional defects in spacetime that, if they existed and moved relative to each other, could create conditions for CTCs. Another concept is the closed timelike curve CTC, a path through spacetime that loops back on itself. An object following such a path could theoretically return to its starting point in time. This idea raises numerous paradoxes, such as the famous grandfather paradox. If you traveled back in time and prevented your grandfather from meeting your grandmother, would you still be born? These paradoxes challenge our understanding of causality and free will. Physicist Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics prevent time travel to avoid such paradoxes. According to this conjecture, the universe has built-in mechanisms that protect the consistency of history, making time travel to the past impossible. While backward time travel remains speculative, forward time travel is supported by current scientific understanding. If we could achieve near light speed travel or harness the intense gravitational fields of massive objects, we could effectively move into the future at a different rate than those remaining on Earth. Quantum mechanics, the science of the very small, also offers intriguing possibilities. Certain interpretations suggest that particles can affect each other instantaneously over vast distances, a phenomenon known as quantum entanglement. Some theories propose that these effects might involve retrocausality, where future events influence the past. However, these ideas are still highly theoretical and not yet applicable to macroscopic objects like humans. Lastly, time travel, as popularly imagined, is a fascinating blend of scientific principles and creative speculation. While traveling forward in time through the effects of relativity is supported by our current understanding of physics, backward time travel presents significant challenges and paradoxes. Concepts like wormholes and closed timelike curves offer tantalizing possibilities, but remain largely theoretical and fraught with practical difficulties. Einstein's theories of relativity provide a framework for understanding how time can be manipulated under extreme conditions, such as near-light speed travel or intense gravitational fields. These ideas have been confirmed by experiments, such as the time dilation experienced by astronauts aboard the International Space Station. However, the notion of traveling back in time raises numerous paradoxes, such as the famous grandfather paradox, which challenge our understanding of causality and the fabric of reality. Theoretical physics continues to explore these concepts, with ideas like the Novikov self-consistency principle and the many worlds interpretation offering potential solutions to time travel paradoxes. Yet, the practical realization of time travel remains elusive. Current scientific theories suggest that our journey through time is more complex and wondrous than simple linear progression. Whether future advancements will unlock the secrets of true time travel remains an open and exciting question for physicists and dreamers alike. Here at InfoBurst, we will continue to explore these intriguing possibilities. Don't forget to like, share, and subscribe for more insights into the wonders of science and beyond.